Hello, welcome back. This is Calculus by Dr. Oz. Today we have two exercises to go through. We are given two power series and we're going to find the radius of convergence for each case. But before we get started, I want to have a quick run through of the definition of the power series, and I'm going to explain that in details within the video. So let's check what a power series is. Here we go. Here is the definition of power series. So if you have x being a variable, then infinite series of the form a sub n x to the n, and if you expand it out for n starting from 0 going all the way to infinity, so you have a0, a constant, plus another constant times x, plus a2, another constant times x squared, and all the way to a n x to the n, and it goes all the way to infinity. So this is called a power series. You can take this as a function because it's a polynomial function, and if you have an infinite series of the form a n x minus c to the power of n, that means this power series is centered at c, and c is a constant, and c may be non-zero. Okay, if c is 0, you go back to the very first form right here. Okay, so in our exercise, we're given 3 of them, and we're going to try to find the radius of convergency. And the radius of convergency is related to the convergence of a power series. When a power series is provided to us, as you see that precisely one of the following situations happen. In the first case scenario, the series converges at C only. And in the second case scenario, we have a real number R such that the series converges absolutely when the absolute value of x minus c is less than R, and diverges whenever x minus c absolute value is greater than R. So what that means is like the radius tells you exactly, the radius R tells you exactly how far you can be from the center of the power series. So depending on how far you are, it determines the convergency of the power series. So this R is important in our analysis, so we have to pay attention to that because we're going to sort of like use the radius of convergency for other types of analyses. All right, so we have 2 exercises, so why don't we get started? All right, this question is asking to find the radius of the convergence of the power series, but before we hit the road, why don't we look at the definition of the power series again? So if you have x as a variable, an infinite series of the form, so the polynomial a sub n times x to the power of n, so this is an infinite sum. If you expand this out, it's a0 plus a1x, a2x squared, anx, and on and on and on. It's called a power series. You can take it as a function, in fact, function of x. And more generally, an infinite series of the form, when you replace x by x minus c, in the description here, so x's are replaced by x minus c. You can see that this is also a power series centered at c. So this is the one centered at 0. Okay, so c equals 0. If c is not 0, then the power series takes this form, okay, and c is a constant. So now the question is like, since you have an infinite series and x is a variable, so the question is like, when is the power series convergent? And in fact, a better question is like, for what values of x the power series is convergent? Okay, so the next slide answers that question. Okay, so for a power series centered at c, precisely one of the following is true. The series converges at c, which is correct, because if you go back here, if you plug in x equals c here, we know that these terms are going to be all 0, and a0 is going to survive. So, well, the infinite series is going to be convergent, for sure. And the second item is that there exists a real number r, positive r, such that the series converges absolutely for the absolute value of x minus c less than r, and diverges for the absolute value of x minus c greater than r. So let's just check what this means, by the way. So x minus c less than r in absolute value means like x minus c is less than r, but greater than negative r, right? Adding c to both sides, so c minus r, x, and c plus r. So we get an interval for x, okay? So in particular, if you have a power series centered at C. Okay, see that I have C minus R here, C plus R here. So now I have a nice interval in the neighborhood of C with radius R. Okay, so item number 2 says that if you choose X in between C minus R and C plus R, that means your X is in this interval, then the series is going to converge. Okay? And if you're outside this interval, somewhere here, right, the series is not going to converge but diverge. Okay? And the third case scenario could be like the series converges absolutely for all X, right? So it's a point convergence, either just converges at C, converges in this interval with finite R, so R is a number, and in the third case scenario, it converges everywhere, right? So there's no R. R is infinity, in fact, right? You can go infinitely many on this direction, infinitely many in that direction, infinitely many units in that direction. So it's in fact convergent for all X, okay? So, and R is called the radius of convergence, as I said, and the set of all values for which the set of all values of X for which the power series converges is the interval of convergence of the power series. All right. So what we're going to do in the first and second examples here, that we're going to try to determine what the radius of the convergence could be. All right. So we have the series 3x to the n, and just to give you some heads up, so this is the very first exercise of this section, power series are generally analyzed by ratio test or the root test. So these are very applicable in that direction. So I'm going to use the ratio test here, and you will see that many times I'm going to keep using the ratio test. Okay, so an is 3x to the n, and I'm treating x like a variable in that regard. Okay, just keep that in mind. So the absolute value of an plus 1 over an is equal to this in the absolute value, right? And this is equal to 3x to the n times 3x, right? I can split that exponent here. And that allows me to cancel 3x to the power of n. So this ratio here is 3x, the absolute value of 3x. Okay? That's good because for this series to be convergent, we want this ratio to be strictly less than 1. Okay, so I want 3x, let me just rewrite that. I want 3x absolute value to be less than 1. So now I'm going to sort of rewrite this in an explicit form to get an interval out of this. Okay. All right. If what that means is 3x is in between 1 and negative 1, and dividing both sides by 3 gets you to a good interval for x, which is that x's are in between negative 1 over 3 and 1 over 3. So what this analysis says out of the ratio test, so this is the ratio test, right? That if you have x's in the power series coming from the interval negative 1 over 3 and 1 over 3, then that any x coming from, in fact, in this interval will make this infinite series convergent. For example, 2 over 3 is within this range, right? I can go ahead and then put 2 over 3 for x, okay? Then it's going to make this, 2 over 3 is not in that range. 1 over 6, for example, in that range, right? So 1 over 6 plugged in, so it makes it like 1/2 to the power of n. And this is a geometric series of r to be 1/2, so this is a convergent series. So what I'm trying to say is the convergence here is coming from the interval c equals 0, negative 1 over 3, 1 over 3. Okay, any x coming from this interval, you're safe, and r obviously is going to be 1 over 3. The interval of convergence, the radius of convergency is going to be 1/3, and the interval of convergency is going to be negative 1 over 3, 1 over 3 open interval in that regard. Okay. Well, you can also analyze this at the end point. We're going to have questions for that, but at this moment, I don't want to bound myself to the analysis of the endpoints, because endpoints are very important once we apply the ratio test here. So what I mean that, can I put equality sign here and here? That's the question. Okay. So I don't want to answer this question because this question is only asking for the radius of convergence. I think we just got the answer that r is equal to 1/3. All right, so you can move on to part B in the next video.